Hello, and welcome to this first part of a two-part presentation on audio loudness measurement and monitoring. My name is Mike Wadeson, and I'm an application engineer here at Tektronix. In this first part of the presentation, we will discuss the basics of the standards and the measurement process. In the second part of the presentation, we'll illustrate how to make the measurements using a Tektronix waveform monitor. Variations in audio loudness between program materials can lead the viewer to reach for the remote control in order to adjust the volume. This can become frustrating for the viewers as they continually have to adjust the overall volume of the programs. Today's digital audio systems have a much wider dynamic range, and a home audio system have high-fidelity audio components, allowing for the full reproduction of the audio signal to be decoded. This can lead to a wider variation of audio levels between programs. While program providers and producers want their program or commercial to stand out from the rest and take full advantage of this wider dynamic range. Therefore, broadcasters and program providers need to monitor the audio programs in order to ensure a consistent audio loudness level between programs and commercials. In this presentation, we'll discuss what the definition of loudness is, and the standards that have evolved to provide consistent measurements of loudness. We will then discuss these measurement methods and standard practices that have been developed for a variety of broadcast and post-production applications. We will show you how these measurements can be performed on a Tektronix waveform monitor, and the necessary configurations of the instrument to make these audio loudness measurements. Finally, we will discuss how these measurement methods can be implemented within a facility. Loudness is a subjective measurement. Different people will perceive loudness differently. For instance, what appears loud to a child may not appear loud to an elderly relative. Loudness is primarily a psychological correlation that we make to the physical intensity of the audio signal. A variety of different techniques have been used to model and correlate the overall loudness level of the signal to compare with what people perceive as being loud. Different filters have been used to characterize and model this perceived loudness of the audio signal by the human ear. When we measure audio loudness levels, the various types of program material will have different perceived loudness levels. For instance, there are different dynamic ranges between radio and television broadcasts, and different types of programs such as music or speech or special effects will have different loudness levels. From a variety of work on loudness measurements, several standards have been developed. Initially, the IEC 61672 standard developed electroacoustic sound level meters that used an A-weighting filter that had a similar frequency response to the human ear. This algorithm was complicated to implement in a system, and the ITU standards body found that a simpler K-weighting filter could be used to make audio loudness measurements. This process was standardized in ITU-R BS.1770 and 1771 that are being widely adopted by a variety of organizations around the world. The ATSC used the ITU standard as the basis for their work on developing techniques for establishing and maintaining loudness for a digital television system. This provides a more practical approach for broadcasters and program providers on how to measure loudness for a variety of different systems. In Europe, the EBU has also developed a standard based on the ITU-1770 standard, called R128. This includes gating measurement requirements to the loudness measurements and definition of loudness range. This standard was developed by the P-Loud Working Group. A set of technical standards, also developed by the EBU, 3341 to 3344, provide additional information. There have been several versions of 1770, and currently the latest revision is -3. The initial -1 document did not include the requirement for gating measurements that were defined in EBU R128. This was added as part of -2 of the document, and today -3 has additional updates to the true peak measurements. The ITU carried out extensive testing to develop the RLB K-weighting filter. This filter is less complex than the A-weighting filter and is simpler to implement within an algorithm or device. The result is a simple energy-based loudness measurement. The LEQK algorithm is based on a high-pass filter that sums the energy over time. This simple approach allows for multi-channel loudness measurements to be made of simple building blocks that are scalable from one to many channels. The lower diagram shows a simple block diagram of a multi-channel loudness measurement. The ITU-R BS.1770 algorithm uses a simple RLB filter characteristic, as shown in the top right-hand diagram, which is a high-pass filter. A pre-filter characteristic is used to account for the acoustic effects of a human head, shown in the lower diagram. Typically, these two filters, the pre-filter and RLB filter, are combined into one algorithm and referred to as the K-weighting filter. Within the ITU 1770 and 1771, a true peak meter is defined. In this process, the audio meters are 4 times oversampled in order to calculate a true peak measurement. You can see from the upper right illustration that if just the audio samples are used by the audio meter, then the audio level may not record the maximum peaks of the signal, and the audio meter may underreport the audio level, especially at high frequencies. The ITU 1770 and 1771 provides a method for measurement of the true peak levels. The basic system of 4 times oversampling is used within the audio meter displays of the Tektronix waveform monitors. The loudness measurement is defined by this equation in the ITU 1770 standard. The channels are defined by the letter I, which is the total number of channels, and can be a single monochannel, a stereo signal, or multi-channel audio, such as 5.1. The N denotes the number of audio channels used in the measurement. Each input signal is filtered by the pre-filter and RLB filter, and is denoted by the value YI. The weighted mean square of each channel is defined by ZI, and is multiplied by the channel weighting as shown in the table. This equation produces the overall loudness measurement. The loudness measurement value is defined in terms of LKFS, that is, loudness using the K-weighting full scale. Here is a simple example of how the values are calculated. If we assume a single monochannel generating a 0 dBFS full-scale 1 kHz sine wave, then this produces a loudness measurement of -3.01 LKFS. From this definition we can calculate a value of Z. If you do the maths, it's 0.5876. Now if we have an audio level of -24.7 dBFS, then using the value of Z within the loudness equation produces a loudness measurement of -20.1 LKFS. This loudness measurement algorithm has been implemented within the WFM and WVR series instruments. In this next section, we'll take a look at the ATSC recommended practice A85. That can be obtained from the ATSC website at www.atsc.org. This recommended practice is based on the ITU 1770 standard and provides a practical implementation guideline for broadcasters and post-production facilities. We will review the parts of this standard within the next few sections. Throughout the standard there are a variety of terms, and we'll start by explaining some of these definitions. An anchor element is the reference point within the program, around which other elements are balanced in producing the final mix of the content. This typically will be some dialogue at an average level, which is neither whispering or shouting. It can also be considered a piece of the content that a reasonable viewer would focus on when setting the volume control. The dialog level is defined as the loudness in LKFS units of the anchor element. Remember that LKFS is defined as the loudness K-weighting value relative to full-scale measurements. The target loudness is specified as the value for the anchor element, the dialog level, that is used to establish facility content exchange from supplier to operator. Dial norm is a Dolby metadata parameter, with a valid value of between 1 and 31. The decoder applies an amount of gain reduction equal to the difference between -31 and the dial norm value. The measurement of the content will depend on the type of material. In the case of program material, with a duration of several minutes, this is classified as long-form content. To measure the loudness of this long-form content, you should find a representative section of the material that is dominated by typical dialogue, that is not shouting or whispering. In the absence of dialogue, the loudness measurement should be made on part of the program that the viewer would focus on to set the volume. Alternatively, the whole duration of the content can be measured. For measurement of short-form content that has a duration of less than a few minutes, then the loudness measurement should be made for all audio channels and all elements of the soundtrack, integrated over the duration of the short-form content. The value of the loudness measurements in LKFS should match the dial norm value of the AC3 encoder when the material is distributed. For a newscast or live programming, the measurement of loudness should be done during the program. The audio mixer of the program should use a loudness meter to help ensure that the real-time content of the loudness matches the dial norm setting of the AC3 encoder when the program is transmitted. For file-based content, a loudness measurement should be made by the measurement device and can be integrated within the file QC process of the facility that will automate the process. Again, the loudness measurement and the dial norm value should be adjusted to match. In order to control loudness between program material and commercial content, it's important to ensure that the dial norm value of the AC3 encoder matches the audio program loudness. A loudness meter should be used to verify the dialogue level of the audio content. When the material is non-conformant, the audio level should be adjusted to the target value. Local stations should receive content at a fixed loudness level from the network or program provider. The local broadcaster should ensure the dialogue level of the AC3 encoder is set to match the network original content. If a gain or loss is applied, then the AC3 encoder would need to apply the offset to the dial norm value. For TV stations that insert local programs, commercials or segments, the dialogue level of this material should match the dial norm value. The network program feed may be decoded to baseband. In this case, the measured dialogue level of this content should match the dial norm settings of the next section of the AC3 encoding process. The AC3 data stream contains line and RF mode dynamic range compression that can limit the overall loudness level. However, these settings should not be relied on for the correct loudness level. Typically, these compression modes are dependent on the dial norm setting being correct within the metadata. If this is not the case, the signal levels could be misadjusted by the receiver. Annex I of the ATSC A85 recommended practice provides a quick reference guide for audio mixers and editors when creating content. In this next section, we'll outline these procedures. For complete information, please download the standard from the ATSC website at www.atsc.org. Audio mixers and editors, when creating content, need to consider the audio monitoring environment that is being used within the facility. Correct setup of the listening environment and ensuring that you're always listening to the audio content at a set level is critical. When mixing the content, the operator should always rely on their hearing and use a loudness monitor as a guide to confirm what they are hearing. it's important that the loudness meter used is compliant with ITU-1770. When generating content and the program delivery loudness level is unknown or has not been specified, the operator should mix to a dialog level of -24 LKFS, with a maximum true peak that is below -2 dBFS. -24 LKFS is defined as the target loudness, and minor variations of up to plus or -2 of this value are expected. You can see the loudness meter scale on the right-hand side image, and we'll discuss this in detail later in the presentation. You should remember that a station's AC3 encoder dial norm will be set to match the dialog level of the content when the program is broadcast. Within the post-production process, it's important to measure the loudness of the long-form content, which is program material that lasts over several minutes. The editor should select an anchor element that is representative of typical dialogue within the program. In the absence of dialogue, content should be chosen that the viewer would focus on to set the volume level. Alternatively, the loudness measurement can be made over the entire content. In short-form content, that is less than a few minutes in duration, it can be difficult to isolate the anchor element. For this short-form content, the loudness should be measured for the duration of the program material. This concludes part 1 of this presentation, as we have discussed the basics of the loudness standard and some of the measurement methods discussed within ATSC A85. In part 2 of this presentation, we'll discuss how to configure the Tektronix waveform monitors to make loudness measurements for EBU or ATSC standards. So please join me, Mike Wadeson, next time for the second installment in audio loudness measurement and monitoring, which is available here on the Tektronix website. And thank you for taking the time to watch this webinar.